Okay, welcome to note set number 14, where we continue with our discussion of sampling, but now we're going to be talking about some practical issues and looking at how A to D converters and D to A converters actually work. We're still in section 6.1 of Proacus and Monolacus. So this is what we saw last time. We saw that, looked at taking an A to D converter, getting some samples, and seeing under what conditions, if we run those samples into a DAC, we can get back an x hat of t that's exactly equal to x of t. And we saw that we could do that under certain conditions. And now what we want to do is look at some of the more real-world issues on how these things work, and so what are the important issues that we have to worry about. And in particular, we'll be talking about quantization issues in the A to D converter, and sample and hold issues in the DACs. So the sample and hold issue will address that assumption that we made that our DAC used delta functions or impulse generator inside the DAC. So we'll see how to take that into account, the fact that we don't really have delta functions there. So here's a picture of a practical analog to digital converter. I'm not going to go into all the details, but the basic idea is that you've got some analog electronics at the front end that's just amplifying some small signal perhaps, and then here's where the sampling actually happens. So you sample the signal and you hold it in place while this digital logic system converts that number into some binary representation, and then that binary representation is either put into a buffer or sent over a bus. So what we end up with is a stream of binary words coming out of an actual A to D converter. And this picture here, I'm not going to go into a lot of the detail, but it does show that there are some issues that surround how long it takes before the hold actually goes into effect. So if you want to get into the details of the innards of an A to D converter, there's a lot of information out there on that, but that's not what we're focused on here. We're mostly going to ignore that aspect and focus on the quantization aspect so that we can understand what impact that has on us from a signal processing point of view. So suppose we've got a signal x of t, continuous time signal, and we put it into our A to D converter. The things coming out of there are b-bit binary words, and b is a parameter that we would buy our A to D converter with some desired number of bits. So typical numbers are 8-bit all the way up to 16, 24, maybe even bigger than that. But those are typical values. And what we'll see is that since we have b-bit binary words, we can only represent certain numbers. In fact, we can represent only 2 to the b different numbers. So those are so it's impossible to represent numbers over a continuum with just b-bit numbers. And so what we're showing here, these vertical dashed lines here, are showing the levels that we're able to represent. And in this case, we're showing 8 different levels, one of which is the 0 level, which you can't really see the dashed line on that. Obviously we'll be using typically more than 8 levels, because that would only be 3 bits, and so a 3-bit A to D converter is really not terribly practical and useful for much, maybe a few applications. But typically we're going to have like 8 bits, so we'll have 256 levels, something like that. Every time I come in here to record one of these, somebody calls on the phone. Well, I'm going to ignore that. So to get a feeling for how this works, we're going to still consider ideal operation, but we're going to consider ideal quantization. So we'll assume that we have an ideal analog to digital converter doing the sampling part of it, and then we have an ideal quantizer. So we'll let B represent the number of bits used to represent the level. So we're going to have 2 to the B quantization levels, and delta will represent the resolution or step size. So that's the spacing between each of the levels. So you can see down here we can represent at delta, 2 delta, 3 delta, 4 delta, and so on. So delta is that step size or resolution. And we can really think of the action of this quantization as a rounding. So we take x, we divide it by delta, and then we round it to the nearest integer, and then multiply by delta, and that gives us the quantized value. So you can kind of see at this point we have something that if we divide by delta, we'll have a number between 3 and 4, but it's closest to 4. So it gets rounded to 4, and then when we multiply by delta, it gets quantized to the level of 4 delta. So the things that we need to think about, or the specs for our A to D converter, are what's the largest voltage that we need to represent, what's the number of bits that we have available. Our resolution then, in terms of those two things, will be 2 times V max, so that's the entire dynamic, the total range that we can cover from maximum positive to maximum negative. And actually we're stretching things a bit because you can actually see that really it only goes down to minus 3 delta versus 4 delta as long as we assume that we have a power of 2 number of levels, which we typically do. And then on the next couple slides we'll talk about something called the dynamic range and the signal-to-noise ratio. So the dynamic range has to do with the range of the weakest signal that we can see relative to the strongest signal that we can see. So if we look at the power of the maximum signal that we can see divided by the power of the minimum signal that we can see. And this is often specified for a sinusoid, just because it's a nice test signal, and everyone can agree upon how that spec was arrived at. So our maximum signal would be a sine wave with an amplitude of full scale, so whatever that full scale representation is. And then our minimum signal would be the smallest sine wave that can actually change the least significant bit. And so that ends up being delta over 2, and you can kind of see the illustration down here that that's showing a sine wave that is just below the level of the minimum signal. It's not getting above delta over 2, so it would get quantized down to the 0 level for every value, and you can see those dots are representing the samples of that signal getting quantized all down to 0. So from the point of view of the A to D converter, any signal all the way up to that point is going to be essentially the same as a signal that's exactly equal to 0. So so we now have a way of specifying the maximum signal and the minimum signal that can be seen. So the maximum signal is just 2b times delta divided by 2. Since we have 2b levels and half of them are positive and roughly half of them are negative. So that's our maximum value or maximum peak value. And to find the power of a sine wave, we square its amplitude and divide by 2. So our maximum power that we can see ends up having that structure. Similarly, the minimum voltage that we can see is delta over 2, and so we square that, divide by 2, and we get delta squared over 8. Now we look at the ratio of those two, and that's our dynamic range, but we typically put it into the dynamic range in dB. And so since this is a ratio of 2 powers, we use 10 log 10. And so we form this ratio, and we can see that there's a lot of stuff here that cancels out. The delta squared cancels, the over 8 cancels, and we're left with 10 log 10 of 2 to the 2b. And if you work that out, it ends up being 6.02 times b. So this is a nice little rule of thumb that for every additional bit, we get an additional 6 dB of dynamic range. And so I've made a little table here showing from 8 up to 16 what the dynamic range is. So you may know that CD audio is done with 16 bits, and so when CDs first came out, you saw a lot of discussion of the fact that CDs had a 96 dB dynamic range, which at the time was pretty good compared to the alternatives. Now, one way of characterizing what the quantization does is we can think of the quantized signal as being the original signal plus noise. Even though it doesn't really physically work that way, we can model it that way. We can think about it that way. What really happens is we round to the nearest quantization level. But once we do that, you can see our values here that have been quantized, and so there's an error, and so we can think about that error as being the quantized minus the original. And I don't know that my actual values that I put here for the error match up perfectly with what I actually have over there, but we do know that the error, the absolute value of the error must be less than or equal to delta over 2. So we've got some characterization of this noise that we can think of. So when we have a quantized signal, even though it isn't really signal plus noise, we can think of it that way. And we'd like to get some characterization of how to think about that noise, how to characterize it. So for this ideal quantization model, the noise that we think about, well, for any scenario, we would like to have a statistical model for our noise. So that means having a probability density function. So that gives a characterization of what's the probability that certain values actually occur. And then the power spectral density, or equivalently the autocorrelation function, that tells us something about how the noise value at one sample location is correlated with the noise sample at another nearby sample location. So it's pretty typical to assume that no error value is more likely than any others. If you think about it, that's basically saying the actual value of the signal is equally likely to fall anywhere in the quantization cell. And so therefore it's quite common to model the probability density function as a uniform distribution. So if you remember from your probability theory, uniform distribution looks like this. And in our case, this will be minus delta over 2 up to delta over 2, and then it has a height of 1 over delta. So that's the actual probability density function. And what I have here is, excuse me, I ran a little experiment. I think I used a sine wave, and I quantized it to a certain level, and then I made a histogram of the errors. And theoretically, this should be flat. but we see that this is pretty close to being flat, and so therefore the uniformly distributed model is a reasonable model to assume. The other thing that we're going to assume is, think about it this way. If I have a sample at the current time and it gets quantized a certain way, if I have a sample at the next instant of time, that most recent past sample, does it have any bearing on how this gets quantized or whether it goes up or down? No. Rounded up or rounded down? No, it doesn't. So, in reality, we can think about that the error then does not affect the error now. Or another way to say that is that the error is uncorrelated from sample to sample. And this is what we refer to as white noise in statistical signal processing. And what that means is that the power spectral density of this noise is flat, which just simply means that if we were to look at how the power of this noise is spread over frequencies, it's equally spread over all frequencies. So these models give us a nice way to try to characterize what the impact of this quantization noise will be on signal processing. So here's some computational results that I did within MATLAB. So the power spectral density, one way that you can estimate it is to just compute the FFT and then take the magnitude and plot it in dB. It's not the best way to estimate the power spectral density, but it's one way. And so I looked at 3 different sine waves added together, and you can see them. Here's 1, here's 2, and here's 3. Okay, so those are 3 different sine waves showing both the positive and negative frequency component of those. And the top is perfect without any quantization. The bottom has quantization, and we can see, this noise floor down at the bottom at a certain height, and we can see that, except for the jaggedness, which just comes from the fact that we're estimating this, that it's fairly flat. It's not going up and down at different frequencies. So that's the white part of this. And so we can see this was for 5-bit quantization. If we used even fewer bits, we would see that noise floor moving up, up, up. And so, understanding how the choice of bits impacts the effect on noise is a good thing to be able to do. And we're starting to get a handle on that here. So to nail that down a little bit more, let's talk about the signal-to-noise ratio due to the A to D converter. So a signal-to-noise ratio is just a ratio of the signal power over whatever noise power happens to be corrupting that desired signal. So in this case, we're just talking about quantization noise. So since we have a uniform PDF for our noise model, it's very easy to find the variance, which is the noise power. We're assuming it's, this says that it's zero mean, so we find the variance of the zero mean random variable, and we just use standard statistical results, and we find that the power due to the quantization with a step size of delta turns out to be delta squared over 12. And so now we can find our maximum power, which we already did before when we were doing dynamic range. And so we can take that max power, divide it by the quantization power, and now the delta squareds get canceled, and we end up with 3/2 times 4 to the b, and if we convert into dB, we get 6.02 b plus 1.76. So that's a characterization of the signal-to-noise ratio. So it means that we get, just like for dynamic range, we get an additional 6 dB of signal-to-noise ratio for every additional bit. Now, that was done for a full-scale sine wave. So that means if I have a sine wave and it's filling up the entire range possible for my A to D, then that's my signal-to-noise ratio. Now, if I put in a weaker sine wave, my quantization noise won't change. That's just set based upon the size of my quantization cell. But my signal power will actually change. So for different scenarios, this SNR result may, or well, this is an optimistic result, and it may have to get discounted if your signal is not full wave, or full scale rather. And so another issue is that this is all, this result that we had was for a pure sinusoid, and you can see that a sinusoid kind of all the time and very somewhat uniformly fills the full range of the A to D converter kind of all the time. But we could have scenarios, we could have signals where, like this one here, where it spends most of its time at, fairly small values, and only every once in a while does it jump up to values that are outside some small range. And so we capture this idea with this thing called the peak factor. So the peak factor is the signal peak value, so this would be the signal peak value, divided by the signal RMS value. And so this peak factor will capture the difference between, for example, these two cases. So the sinusoid has a low peak factor, and something like this, where it might be somebody talking quietly, and then they shout, and then they talk quietly, and then they shout briefly. That's something with what's called a high peak factor. So to see the impact of this, I made a little plot here, and this is just showing. This is for full scale signals only. And so the SNR, you can see as a function of the peak factor and as a function of the number of bits. So assuming that our signal is a full scale signal, and for these different number of bits, we can see the impact of the peak factor. As the peak factor goes up, the SNR goes up as well. And also should be pointed out that these peak factors are in dB, and the largest peak factor that any signal can have is minus 3 dB. So this is just something to keep in mind, that if you are trying to quantize or sample a signal that is very peaky, your signal-to-noise ratio result will be much less than what you would expect based upon thinking that you're quantizing a sinusoid. So there are some other errors that crop up, even more than what we're going to mention here. In fact, you could build an entire career just fussing about errors in A to D converters. But we're just interested in, kind of presenting some of the key ideas. So there could be some nonlinearities. So, the electronics that take the input signal and get it to the point where it actually gets quantized can have some nonlinearities in it. So we think about plotting, the ideal case here would be red. Every output value that's about to be quantized, just the red just maps it perfectly linearly from the input value. But the blue shows some nonlinearity there, a small amount, but still that could be significant enough to worry about. Then there's something called aperture jitter. So that has to do with the fact that you're using a clock to tell the A to D converter, take a sample now, then take a sample now, and now, and now. And so the circuitry that we use to say now, that can be fluctuating, but also the circuitry inside the A to D converter, once we say now, it could be a random amount of time between when the clock hits and when the sample is actually taken. And so that is called aperture jitter. And then sometimes there's just by the nature of this, there's a binary code that will never properly show up regardless of the input value. So that's some sort of error occurring inside the A to D converter. And so these three things, especially the nonlinearities, the aperture jitter, and the missing output code, cause a couple additional errors. So one is called spurs in the frequency domain, and we'll look at that briefly in just a bit. And then the other is the other thing that it causes is I say increase. This should be a decrease. Decrease in the signal-to-noise ratio. Increase in the SNR would be nice, but no, this should be decrease in the SNR. So here are some effects of this. We have our three sinusoids again. So there's one here, one here, one here, and here are their negative frequency components. And then all these other spikes that stick up significantly above the noise floor, those might be considered real signals, but we don't really know for sure in a real application. So they stick up and they look like they could be, real spikes. We don't really know. So if you look at a spec for an A to D converter, you'll often see something spec'd as the spurious free dynamic range, SFDR, and that just says that it sets kind of this distance here. That's kind of where you have, that's the range where you can have your signals show up without worrying about getting buried by some of these spurs. And then we have the noise floor down below, and that could be elevated more than what it would be from a pure ideal theoretical point of view. So if you look on a spec sheet for a practical A to D converter, and they're not hard to find, you go to the usual suspects who sell these things, the integrated circuit manufacturers, and you download their spec sheet, and they'll tell you an awful lot about them. But they'll tell you something about the signal-to-noise ratio, and it's important to know that these are usually fairly common definitions, but you should check the data sheet. But typically, when someone talks about the signal-to-noise ratio, they're not including the power of the spurs in this SNR computation. And then there's another thing called the SINAD, which is the signal-to-noise and distortion ratio. Excuse me. And that's just a signal-to-noise ratio characterization, but now the noise power includes the power of the spurs. So this SINAD is used to define this thing called effective number of bits, or ENOB. So the ENOB is a favorite spec that people will look for to give an idea of the quality of the A to D converter. So once we have our SINAD, and remember that includes the power of the spurs, we just treat that in our theoretical characterization of form for our SNR. So if you remember, the SNR was 6.02, So let me write it over here. 6 dB times B plus 1.76 was equal to the S and R. So if we set that equal to SINAD and then solve it, not knowing what B is equal to, solve it for B and then call that B ENOB, you can see that this is the algebraic solution of that. So it just gives a way of characterizing, since SINAD kind of gives you a characterization of all the badness that's included, that's going on in the A to D converter. Then you convert that into this effective number of bits. It says this A to D converter has some imperfections that are making it might be a physical 8-bit device, but it may only look like a true theoretical 6-bit device, in which case its ENOB would be 6. Spurious free dynamic range we defined already graphically on the previous page. So these 4 specs are things that you'll almost definitely find on the spec sheet for an A to D converter. And so if you're looking for one for an application, you're going to want to look at these things and have some idea of what it is that you're looking for those specs. So now let's turn our attention to the practical D to A. So we've got samples coming in. We had talked about coming into an impulse generator in our ideal DAC, and then going into a continuous time low-pass filter. But the practical D to A basically takes these binary words that are coming in. We need something that will convert the binary word into an appropriate voltage. So that's pretty easy to do. You just have some circuitry that converts binary number into an appropriate voltage. Then we have a sample and hold, and basically the sample and hold just is the thing that builds not an impulse but a regular pulse. So if you remember, we talked about the pulse being this little rectangular pulse, and you can see here that what's happening, let me pick a good one, what's happening is that we are making the pulse capital T, where T is our sample spacing. We're making the pulse capital T seconds wide. So you hold it until the next value comes in. And then we run this through our continuous time low-pass filter to try to smooth it out and create the curve that the samples represent. So that's just pictorially how this works. And what we need to do is analyze the impact of this this practical scenario. So here was our ideal case, and we saw how to analyze that. We had our impulse generator, and we figured out what the Fourier transform of this was, and then we analyzed in the frequency domain the impact of that low-pass filter. Well, what we can do is take instead of having the pulse generator generating these pulses that are capital T wide, we can still think about an impulse generator, and then think about a system here that has an impulse response of its own that is just rectangular of width capital T. And so if we put a delta function in here, we'll get one of these rectangular pulses of width T out. And so if we're putting in a sequence of these things, we'll get a sequence of these pulses out. Oops, I shouldn't have drawn it like that because I'm trying to make it capital T. So then our next one would start right adjacent to that. And so on and so on and so on. So this setup models what's really going on in the real world DAC, but it also sets it up for easy analysis. So we now have an impulse generator. We already know what that signal looks like. That's the same thing. Now, instead of just going through a continuous time low-pass filter, we're going through, this shouldn't be, I'm sorry, this should be T, not N. Now we're going through a continuous time system with a rectangular impulse response cascaded then into our low-pass filter. So we can do this analysis. Well, up here we did an analysis with x tilde of omega times h of omega. Now we're going to down here do x tilde of omega times the sample and hold. I guess I didn't need that tilde on there. Some sample and hold transfer function or frequency response, and then into our filter frequency response. So this is the frequency response of this, H is the frequency response of this. And that's how we're going to rise this. So here's a picture of the ideal case, just reminding you of what we talked about in the previous set of notes. And then here's how it works with a DAC with sample and hold with a width of capital T. So we start off with this. That's what's actually happening at this point. So that's we've got the replicas and all of that, as we saw before. And now instead of that going directly to a low-pass filter, it's going through the sample and hold. And if we find the Fourier transform of a rectangular pulse, we find that it has a sinc function look to it. It is a sinc function. And so we see that what's happening here is we've got some amount of roll-off, and this goes all the way out to Fs. So then we design some filter here, and we kind of design it so that it swoops in such a way up to try to compensate the fact that that's swooping down. So our goal is to try to retain the exact perfectness there, but we also have some of this together with this allowing some of the spectral replicas to come out. So some of that can come out. So it now becomes an issue of trying to design these things just right. Now, one way we can combat this is by using oversampling. So if we oversample, remember, our spectral replica gets moved farther out. Our sample and hold is much broader, and in the range that we're interested in, notice that this thing is really, really flat, so we don't have to necessarily correct that much. And by the time we get out to here, where we might see some of this start to come in, this filter can be designed to be very, very low. So there are some advantages to sampling significantly faster than what Nyquist theory or Shannon theory says. Now, just one last comment here on this. There are ways, once we have this x of n, to artificially increase the sampling rate. And this is what's known as multi-rate signal processing. And I don't know if we're going to get to that later in this course or not. We'll see whether we have time to do that or not. But basically, you've already got enough samples to completely reconstruct this, so why can't you perfectly, or at least quite almost perfectly, reconstruct more samples? If you can reconstruct at every value of t, you can reconstruct at points in between those samples. So there are tricky ways to increase the sampling rate. So now, without actually having an oversampling A to D converter, we can upsample before we run into our D to A converter. Now, you don't see this marketed this way so much anymore, or at least I haven't noticed it. I haven't been in the market for a CD player in quite a while. But when CD players first came out in the mid-'80s, in the late 80s, and into the 90s, there were a lot of them that used this artificial oversampling technique to effectively enable an easier design of this filter. Let me clear some of this stuff off here so that it's a little easier to see. But the idea is that if you artificially upsample this, now you can you suffer less from the sample and hold, and you need to do less work to try to make that thing correct for the fall off of the sample and hold. In fact, maybe you don't have to do any work at all. You can just use a very, very simple filter. So these oversampled CD players and were touted as being good, good examples of CD players, and you'd see them marketed. They came out, this one is 4 times oversampling. Then someone else would come out with, this is 8x oversampling. And someone else would come out with one, this is 16x oversampling. And to some degree, yes, the higher the oversampling did actually give you better performance because it pushed these spectral replicas farther out, made this flatter during, over the range of frequencies that you were interested in, and made it easier to design this. But the reality is that if you worked hard at designing this, you could get a really excellent result without doing this oversampling trick. So in some sense, this oversampling hype was being used as a way of saying, we played this trick so that we could get good performance cheaper, which I suppose is a good marketing thing. We're going to give you good performance at a lower cost. But there were some CD players that didn't play the oversampling trick and sounded just as good as the ones that did play it, but they tended to be perhaps a little bit more expensive. Anyway, this is a neat way to think about A to D converters and D to A converters. And one of the big things that you should be taking out of all this is how we go from, actual physical devices that are doing things and come up with models that are at least reasonably accurate so that we can come up with some nice mathematics and theory that guides us as to why this works, how does it work, and what are the trade-offs. And that's what engineering is all about, and that's what signal processing engineers do every day. So we'll stop there, and I'll see you next time.